Okay, so welcome everyone. Thanks for coming to this symmetry seminar. This is the first installment of a meeting about all aspects of generalized symmetries of all kinds of making. The seminar is thought to be somewhat an informal seminar where we have lots of discussions. So it shouldn't just be 1 hour of one speaker talking to us, but you should ask as many questions as you like. You can just unmute yourself, raise your hand, do all these things. And we ask the speakers to actually be, not rushed while they're speaking. Okay, so our first speaker is Michele da Zotto from Uppsala, and he will speak about, and now it's your turn to tell us the title, which is
generalized symmetry, global structures from the infrared.
Here we go. Yes. Okay, so if you screen share, please.
All right. So can you see my full screen?
Absolutely, yeah. Thanks. So take it away.
Okay, thank you very much for inviting me to this seminar and for organizing it. It is a pleasure to see this excitement about these topics, and I'm glad to be given the opportunity of presenting some of my recent thoughts about the subject in this occasion. This is based on an ongoing work that I'm preparing together with Iñaki that will see the light relatively soon, I hope. Depends on various circumstances. It might be delayed or not, but it should appear very soon. And then it's also based on a series of other works that I've wrote in the past 7 years, more or less, that will enter more or less in various parts of the talk, and mostly I want to highlight recent work with some of my students. My student Robert Moskrop, who did really great on this project, and Shani Mainet, who is a recent postdoc in our group. And so let me start with a little disclaimer about the referencing for this talk. There have been a lot of activity, and so there are many, and I might have missed some. So apologies if that is the case. If not, well, I hope I will acknowledge your work consistently during this seminar. So before I start, there is a small commercial break, which probably some of you have already seen. There is a workshop and a school on global categorical symmetries in June at Perimeter. These are the dates, 6 from 17. The first week will be a conference. The second week will be a school. So if you have students, PhD students, young postdocs that you want to send us, please do. The registration will open soon, and there will be a selection of the candidates. And there is also a workshop on Argyres symmetry, quantum field theory, and geometry that I'm co-organizing with Sakura that will happen at the Simon Center for Geometry and Physics. And for that one, the registration is open. So if you're interested in coming, please submit an application. And the dates are September 19 to 23. All these informations plus other things can be seen on this website for the collaboration on global categorical symmetries. So I thank you for your attention on this small commercial break. And now we can finally dive into the talk. As an executive summary, so that you know more or less what we are going, recently there have been a lot of results about application of geometric engineering techniques, the global structure of non-Lagrangian superconformal field theories in various dimensions by many people in this audience. And essentially they all involve an interplay between defect groups or defect operators captured by non-compact cycles wrapped by D-branes in string theories, and corresponding Heisenberg algebras generated by Fried-Moore-Segal fluxes. These are non-commutative algebras that arise. And so today, what we were interested in is to give an infrared field theoretical understanding of these Heisenberg algebras. So we get them from geometric engineering in that context, and the results from geometric engineering reproduce results that we know from Lagrangian field theory. but many times we also have results about non-Lagrangian field theories. And in that case, it is interesting to try to see if there is an understanding of the same results from a slightly different perspective. So that's the plan for today. The structure of the talk is that I will begin with a review of this recent construction about the symmetry TFT by people in the audience. And then I will move on to a review of geometric engineering. And then I will get to the core of the talk, and I will discuss how this interplay of global structure and infrared comes about. So first part of the introduction, it will be about the symmetry TFT, and this is based on some unpublished seminars by Dan Fried and a beautiful paper by Abruzzi, Bonetti, Garcia-Estebarria, Shagar-Hosseini, and Sakura that was out last year. So I refer you to the paper for this part. So the idea is the following, right? Constraining RG flows is a very interesting open problem in quantum field theory. This is something that goes without saying. Starting from an ultraviolet phase, we flow to the infrared, and we might flow to different infrared points according to the type of relevant deformation that triggers this RG flow. And these typically give rise to phase diagrams for the infrared phases. And it will be interesting to understand how to constrain this phase diagram. And one well-known idea in field theory is to look for properties that are robust against RG flows. Robust meaning that they are the same in between the ultraviolet and the infrared. Main example from the 80s, paper by Toft, anomaly matching. A modern perspective on anomaly matches comes about from a perspective that in our community we call inflow perspective, in which we start from a quantum field theory in d dimensions, and we see it as if it has attached a topological field theory in one dimension higher, which is an invertible field theory, which means that it has a one-dimensional Hilbert space. And this invertible topological field theory is essentially responsible for capturing the anomaly of the quantum field theory on the boundary. This is this inflow mechanism. The idea is that you have to think about an invertible TFT as something that computes a phase for you. And this phase is essentially compensating the phase that the partition function of your quantum field theory picks up once you perform background gauge transformations. And in this way, the inflow essentially makes this setting into something consistent instead of being just a section of a line band. So about this, there is a beautiful paper that reviews this topic, which is by Dan Fried of 2014. In which he discusses the details of this construction. But for today, so one thing about this anomaly matching is that the TFT matches between the UV and the IR phase. So if we start from an ultraviolet phase and we flow to the infrared, the invertible TFT in the bulk stays the same. So this is the anomaly matching from this perspective. This invertible TFT is something which is robust. It's an example of something which is robust against RG. So this picture must generalize when our quantum field theory has a global structure. So what do I mean by global structure? I was asked by Lakshas to be kind of pedagogical, so we'll try to at least to be a little bit. So the idea is that you have to think about the fact that there are quantum field theories that have identical local dynamics, but that differ globally. What do I mean by saying that they differ globally? An example, let's think about an example to explain this concept. If you take n a prime number, you have two versions of the SUN theory. The one with gauge group SUN and the one with gauge group PSUN, which is SUN modded out by its center. And you see, like, how do we distinguish between quantum field theory? We distinguish exploiting observables, for instance. And if you take the 4D n equal to 4 supersymmetric version of these gauge theories, there are observables that we can compute exactly. An example are these Vafa-Witten partition functions. And these are captured by a sum over bundles for the groups SUN and PSUN. And indeed, if you think about the global structure, the sum over bundles in between these two theories is different. They have different bundles. The sum is different. we can use this Vafa-Witten partition function to distinguish in between these theories. And this is a result by Vafa-Witten of 94. And so from a more modern perspective, we can say that these theories have a different higher form symmetry. They have a different spectra of higher dimensional defect operators. And we can use those as a diagnostic for the global structure. This is something that was discussed in 2014 by Gaiotto, Kapustin, Seiberg, and Witten in a seminal paper on this subject that is also responsible for many of the activities that followed. So reading between the lines of these gauge theories, which is a citation to a reference to another paper by Aron, Tachikawa, and Seiberg, unveils this difference. So the lines that are genuine in one theory are non-genuine in the other, and vice versa. So no worries about if you don't understand what I mean by genuine and non-genuine. We will encounter more concrete examples in the rest of the talk. The idea is essentially that if you think about an extended operator, if it is a line operator, for instance, and it is defined intrinsically by the line over which it is supported, then that operator is a genuine operator. But sometimes you have operators that, in order to be well defined, needs to be attached also surfaces, if they are line or higher dimensional membranes, if they are or other types of extended operator, and those are non-genuine operators. So, but we will see more explicitly what I mean by this in the following. And here again, references for this terminology is a paper by Kapustin and Seiberg of 2014. I think they are the responsible of the distinction between genuine and non-genuine operators. So the question is, how does this picture generalize when a quantum field theory has a global structure, right? The idea is that in that case, this anomaly TFT enhances to a construction that involves a symmetry TFT. Okay, so I'm sorry, my ability of drawing are not. It's more like a Picasso description of this. So, but I hope it gives. I hope it gives the idea. So the idea is essentially that the Hilbert space here becomes higher dimensional, and the various global forms of the QFT on the boundary are captured by the choices of states in the Hilbert space of this TFT. So here, essentially, we have instead of having an anomaly theory, we have some sort of an interface, which we can think about like a gapped boundary interface, in which we fix some Dirichlet boundary conditions for the field in the symmetry TFT, and this choice must somehow lock the global structure of the quantum field theory on the boundary. Okay, and this is a perspective that, again, I refer you to this unpublished notes by Fried and to this nice paper by Abruzzi, Bonetti, Iñaki, Chagar, and Sakura.
Michele, can I ask you a brief question?
Yes, absolutely.
You have two boundaries. You have QFTD, and then on the left, you say gapped boundary theory. So are you talking about two boundary theories?
Yes, the idea is that in general, when you think about an anomaly, you think about the TFT in D+1 dimension as something that extends at infinity. Here, if you have this global structure, then between the anomaly and the quantum field theory, you have to sandwich like a small interval in which you put your symmetry TFT. It's like this construction is essentially responsible for explaining how to couple an anomaly with the theory on the boundary. It's kind of selecting the global structure.
So the yellow is the anomaly theory?
Yes, it's like there is an interface between the symmetry TFT and the anomaly.
I see. Got it.
Okay, good. Thank you for clarifying. I'm sure many people are probably equally confused by my awful drawing. For a beautiful picture can be found in the papers by Iñaki and Sakura and collaborators. So
Michele, I have a question.
Yes.
So what happens if Fabio. Flow?
Hi, Fabio.
What happens if the Argyres flow breaks the symmetry that you're studying the anomaly of? Like either spontaneously or explicitly.
Well, that will be reflected by the way in which the symmetry TFT couples to your background fields. Like so the QFT on the boundary couples to the symmetry TFT via background fields. So there are background fields for the symmetry on the boundary, and they become dynamical in the bulk. Okay, and then whatever happens on the boundary will be kind of reflected by the behavior of these background fluxes and therefore imported. So of course, anomaly match all the time. You don't, even if you break the symmetry, anomaly are matching.
Right, but usually you need also to include either like the ghost of bosons or
yes. That's
the spurions.
That's part of the definition of what I put on the boundary, right? It's not you need to include everything in a sense. Does this address the issue?
Thank you.
Thanks. So the idea is essentially that these choices of global structure for the QFT on the boundary are in kind of explainable in a sense, exploiting the Hilbert space of the symmetry TFT. This is the slogan that I want to convey. And so if we consider an RG flow, then this structure is robust against RG, but it is this whole structure which is robust. So of course, if you flow to a phase in which to match the anomaly, you need to include extra sector in the infrared, then you have to keep track of the whole dynamics of the IR, and then it becomes robust.
Well, I have one complaint.
Yes.
I think the QFT, the thing you're labeling QFT as one of the boundaries should be called a relative QFT.
Yes, I agree.
Because it has defects which are not local with each other.
They are not mutually local. Yes. So I agree. Yes.
And the QFT is a compactification, the interval compactification
of this. Yes, of this picture. Yes. Thank you, Laksha, for clarifying this. Yes. So if you have a global structure, then typically you have a relative field theory. In order to get an absolute field theory, so one that assigns numbers to d-dimensional manifold, you need to prescribe this vector in the TFT, right? This you need to prescribe a state in the Hilbert space of the TFT, which is done by this sandwich procedure. So part 2 of the introduction are about this recent development on geometric engineering and global structures. This builds on several of the works that I cited in the beginning, but also on a very nice paper by Dave, Sakura, and Brian of 2020. A lot of works by the Oxford group between the 2020 and 2022. These are some of the names of the people involved: Fabio, Laksha, Antoine, Cyril, Simone, Max, Yuan, all these people. There is also a lot of activity from Penn, Miriam Chuetic, Riegel, Lin, Jonathan, Hao Zhang, more or less in overlapping period. And then we have this recent paper with my student Robert, Shani, Jonathan, and Hao. But more or less, what is the philosophy? So this is a famous quote from a paper by Coulomb-like of 97, which is essentially that it says essentially that geometric singularities of the internal compactification manifold encode a great deal of information about quantum field theory, but we can turn things around. And if we turn things around, then we can essentially develop a program to study quantum field theory in terms of geometry. So it's a program to study quantum field theory. This is what I wanted to emphasize in this context. We establish dictionaries between geometric singularities and the theory of quantum fields. Well, to be honest, we do it with supersymmetric quantum field theory. It's volume 3, not volume 1. But the dictionary, in this case, we can kind of control it. Otherwise, it's a bit more sketchy. But there have been attempts.
So this slide is Picasso.
Thanks. I take it as a compliment, but perhaps not to Picasso. so back to Picasso. What happens if we apply the dictionary to this picture of this symmetry TFT? Well, the idea is essentially that the results on the symmetry TFT can be read off from an interplay with non-commutative Fried-Moore and Segal fluxes. These are Fried-Moore and Segal. This is a work of 2006, a couple of works of 2006 where these ideas were developed. So again, sketchily, what is the philosophy? The idea is you start from your favorite string theory, which I denote S, and your QFT on the boundary is obtained by considering the geometric engineering limit of this string theory on your singularity X. And then the symmetry TFT becomes captured by some sort of a topological sector of the string theory, which now is no longer compactified on X, but on its horizon, on the link of the singularity. Okay, and then this prescription of a state in the Hilbert space of the symmetry TFT is kind of interpreted in geometric engineering in terms of this Heisenberg algebra of non-commuting fluxes. The Heisenberg algebra is what gives the Hilbert space a non-trivial dimension. Then what is the idea? There is a little aside. This picture is not, it's a holographic picture of symmetry, and it originated indeed in holography. So there is a beautiful foundational paper by Aharoni and Witten of '98, and then there are follow-ups by Bergman and collaborators, and also a nice paper by Fabio, Marek, forgot the name of Gould, unfortunately, and Sakura of last year. In which how Dowie, thank you. Thank you. I've never met him in person for the moment. So this is this holographic picture. And so what is the idea? You start from a stack of ND3 branes. Consider the case of for d n equal to 4 SUN superior mills. We decouple the center of mass for simplicity. And you start from your stack of ND3 branes, you perform a holographic limit, and you end up with a picture which is a DS5 times S5, but now S5 has n units of G5 flux. And if you look at the topological part of type 2b, there is a term which involves this B2 and then the C3 Ramond-Ramond potential wedged with this C5 on this space-time. And when you integrate the G5 on the S5, you end up with this n in front of this term, and this term becomes essentially responsible for the possible choices of global structure holographically in ADS5. So I'm being a bit sketchy. I'm hiding some details under the rug, but this is more or less the philosophy, and I just wanted to use this opportunity to highlight a possible term in this symmetry TFT that is responsible for this global structures. So of course, this is not the whole symmetry TFT. This is just a little term, one of the terms in the action. There might be more, and the more there are, the better. The more interesting it becomes, and the more interesting the interplay between the global structure, the symmetries, and the anomalies that results from this picture becomes. So as far as this holographic description of symmetry, the results reproduce the known results from gauge theory. For instance, it's very nice to see how the various possible global form of SUN theory can be realized exploiting this dictionary. And it also predicts results for quantum field theory that don't have a conventional Lagrangian description. It's a prediction, however, and then there is the question, this prediction is sometimes puzzling, and for instance, if you think about SUN n equal to 2 superior mills, it has a ZN one form symmetry, and you can give vebs to operators in the adjoint and flow to the Coulomb branch. So this is a puzzle that was brought to my attention by Thomas Dumitrescu. Go to the Coulomb branch. You go there by giving vebs to operator in the adjoint, so you don't expect to be breaking the one-form symmetry, center symmetry. However, you can tune the parameters of this theory to get to an Argyres-Douglas CFT, an AN-1 if you start from SUN. This theory, the first example was constructed by Argyres-Douglas in '95, and then this whole family of ADE example was built exploiting geometric engineering techniques by Eguchi, Ori, Ito, and Yang in '96. And so this Argyres-Douglas theory, if you exploit the geometric engineering dictionary, I mean, naively, you see from this field theory argument, one would expect that this Argyres-Douglas theory have a one-form symmetry, have a center one-form symmetry. You just tune operators in the adjoint, you are not breaking the symmetry. However, if you use the geometric engineering, you find that they don't. They don't have a one-form center symmetry. There is no analog of that. So how comes? And for this reason, like, it would be interesting to develop techniques to check these predictions. And this was one of the motivations for this project with Iñaki. So is there a way to check the prediction of this geometric engineering dictionary? And you see, the point is, as I emphasized at the beginning, so the idea is that these non-Lagrangian QFT often have some infrared phases that are under control. And whenever that happens, we can exploit them. So in the case of these Argyres-Douglas theories, for example, they all have a Coulomb phase. And in the Coulomb phase, then we can exploit the dynamics of Maxwell theory to kind of reproduce the results from geometric engineering in a way that we kind of understand in terms of field theory. And so exploiting these phases and the robustness of the symmetry TFT, we can then give rise to this explicit consistency check for the results of geometric engineering, which is the topic of this project with Iñaki. So this is when the talk really starts. It's based on this ongoing project with Iñaki, and then there are many other references here. Some that are not ours are this beautiful paper by Gaiotto, Moore, and Knightsky of 2010, where they really somehow see this type of perspective. They have an understanding of what is going on for four-dimensional theories. This paper by Aroni, Saiver, and Tachikawa that I mentioned earlier, some of my papers, a paper by Ceccotti and Caorsi of 2017, in which they kind of recover these defect groups. They call them toothed groups, but they are essentially the same. And then papers by Laksha and Sakura of 2021 about 5D and 6D examples. And then a very nice work that was published on the first day of the year by Laksha, Simone, Max, and Sakura, where this idea, this understanding that also Laksha emphasized before of the difference between absolute and relative quantum field theories and their interplay with defects that are not mutually local or that give rise to a global structure, was discussed in detail. So for concreteness, right now, let us focus on the four-dimensional case. And I will comment a little bit how this can be generalized to 5D and 6D examples. And so in 4D, a Coulomb phase is a phase in which we have an infrared description in terms of R copies of the U1 Maxwell theory. So R copies because R would be the rank of the CFT, it's called the rank of the CFT. And there are R U1 Maxwell fields that are independent one another. And so we expect naively a symmetry enhancement, right? We expect that at generic point on the Coulomb branch, we expect to find an electric one-form symmetry and a magnetic one-form symmetry to the power R, if we are being naive. So for concreteness now, for the sake of the discussion, let's take R equal to 1. We can write down the coupling to the two-form background fields for U1 Maxwell, and following an appendix of a paper by Clay Cordova, Thomas Dumitrescu, and Kenny Triligeter of 2018, one can literally find the action for Maxwell theory. Everything seems straightforward, and one can write a coupling of this form. Here you see I have to shift F by the background two-form symmetry, by the background two-form for the electric one-form symmetry, because the photon is a Goldstone mode for this spontaneous symmetry breaking, and instead the coupling to the magnetic part of the magnetic background is similar to a minimal coupling like the ones that we are familiar with from quantum mechanics. So this is the form of the action of Maxwell theory in presence deformed by this background two forms. I have the B2E for the electric one-form symmetry and B2M for the magnetic part. We can perform background gauge transformations, which would shift the photon with the electric one-form symmetry parameter, and the background two-form for the electric and the magnetic would shift by the differential of the one-form symmetry parameter. And what we obtain is that this action that I wrote down shifts and it picks up a term. This term is a mixed Tooth anomaly between the U1 electric and the U1 magnetic and it essentially says that we cannot gauge both, right? There is an obstruction in gauging both. So in presence of this term can be cured by an inflow, and the inflow gives rise to this 5D action, which has already a form which is reminiscent to the one that we found holographically. You see that there is a two form wedged by the D of another two form, an electric and a magnetic, that are on the boundary would become the electric and magnetic background, but in the 5D theory they would be dynamical. Well, dynamical is a topological field theory, so dynamical must be taken cum grano salis. So this U1, however, this enhanced symmetry is broken explicitly by the presence of massive charged dionic states on the in the spectrum, and the breaking of a higher form symmetry goes more or less as follows. So if you have a line with a charge Q and you act with a topological symmetry defect on it, it acts just by shrinking on the line that it is linking. And upon shrinking it, it transforms it with a phase which is proportional to the charge of the line. But if we have a massive charged states in the spectrum, then these lines can end. And when they can end, then it can happen that we can essentially, since these symmetry defects are topological, we just slide them off the line, and then by the fact that they have this topological support property, we can shrink them down to nothing, and we end up with an equation like this. So this equation essentially is responsible is true only if this identity is valid. So only if we get a root of unity. I'm sorry, I cannot. Okay. And this is responsible for the breaking of the U1 to a ZQ one form symmetry. So this one form symmetry, therefore, the presence or absence of a one form symmetry is explainable in a sense in terms of the completeness of the spectrum. Where here I have to give a little caveat. I'm using the term completeness of the spectrum in a way which is slightly different from the way in which it is used in the swampland literature. For me, completeness of the spectrum is related to the Tooth screening mechanism that we just reviewed, and the spectrum is complete if I have enough dynamical states to screen the charges of all the lines. If I don't, then I'm left with some higher form symmetries because I cannot screen all possible charges. So there is a well-known generalization of this effect in presence of both electric and magnetic charges, which is this Tooth screening mechanism that was brought down for ordinary gauge theories by Tooth in 79. Beautiful series of papers. So so let's go a little bit in detail about how this works. You start from the charge lattice of the theory. And since you have R copies of Maxwell, then you have R electric charges and R magnetic charges. Okay, and so the charge lattice of the theory is the set of charges in this lattice that are effectively populated by actual stable particles. So you can view, exploiting this philosophy by Gaiotto, Moore, and Naitzke, you can view the line defects as if they are heavy probe particles. Okay, for our theory. And now the question is, if they are heavy probe particles, which one can we allow in our system? And of course, we must satisfy Dirac quantization. So if we want to constrain the spectrum of possible lines in 4 dimensions, then we start from the charges in our theory. We take gamma in our charge lattice, and we constrain the lines by the requirement that their Dirac pairing between the elements in the charge lattice is an integer. Okay, but when we perform this, when we do this, we essentially are defining a dual lattice. Okay, this relation is like a duality, and if we take 2 charges in the dual lattice, then it can happen that they don't have a an integer Dirac pairing any longer. Okay. So this is the statement that these 2 lines are not genuine one another. They are not mutually local, as Laksha was saying previously. How do I view this? So the idea is that if you take one line with charge alpha, another line with charge beta, when you perform a monodromy, they will pick an Aharonov-Bohm phase, which is proportional to their Dirac pairing. So if that Dirac pairing is an integer, then we don't see the Dirac string, and they are genuine lines. They are mutually local. If instead this Dirac pairing is not an integer but is a rational number, then we can measure the Dirac string, and this is a problem. We cannot include, therefore, all the charges in the dual lattice, but only the maximally mutually local sublattices that we can write, and only those avoid to avoid this problem. So instead of looking at the whole set of dual charges, we have to choose a maximal collection of charges that satisfy this condition, that satisfies that the Dirac pairing is integral. So this was discussed by Gaiotto, Moore, and Knight back in 2010, and the global structures that our gauge theory has are essentially in one-to-one with these inequivalent choices of these lattices of defects. And if we keep track of the screening mechanism, then we end up with this Aharoni Seiberg Tachikawa reading between the lines story. So let me just discuss an example of SU2 Superior Mills so that this becomes clear. If we consider the Seiberg-Witten solution of this theory, we see that it has a dion and a monopole as the generators of the charge lattice of the spectrum of states. And now consider adding lines and requiring that they have charges that have a Dirac pairing that is an integer. If you do that, then you find out that the charges of the lines are constrained in this way. And in particular, you see that x2 can be a fraction. It can be a half integer. So this is weird, right? We started from Maxwell theory. We end up with a half integer line. That's very strange. So and if you look at these possible choices, you see that depending on which of the following generators for the dual lattice you choose, you end up with different global forms of the theory. If you choose to have a genuine electric line, then you end up with the SU2 lattice. If you choose to have a genuine purely magnetic line, then you have SO3+. And if you have a dionic line as a genuine one, then you get SO3-. Okay, so this is how these choices of different inequivalent lattices give rise to these choices of different inequivalent global structure. But lo and behold, this involves including in Maxwell theory charges that are wrongly quantized. So if you start with the ordinary Maxwell theory as I presented it at the beginning of this part of the seminar, we were essentially implicitly assuming that the lines were all quantized over the integers. And instead, this infrared perspective is suggesting that no, here we are using a Maxwell theory with a different choice of quantization for the lines. And it is this difference which dictates how to modify the inflow mechanism. How to modify it? Well, it is essentially it's essentially we modify it in order to keep track of this non-integrality condition. And a way to do it in a way which is covariant with respect to electromagnetic duality is to deform the inflow term that we were getting at the beginning of the talk from just the ordinary Maxwell theory. We deform it with a term which is proportional to the Dirac pairing between the generators of the charge lattice of the theory. If you deform that 5D action with this term, then you can you obtain a 5D TFT, which has the features that you need to recover the global structures. Let's see how it goes. So you can, since Q alpha beta is a matrix, an antisymmetric matrix with integer entries, it is always possible by field redefinitions of BE and BM to put it in a form which is like this. And then this 5D action becomes a sum over R copies of a BF theory. And this is a BF theory that has levels, these integers nk that we compute from like what in these geometric engineering papers is referred to as the Smith normal form of the intersection pairing. So the quantization of this BF theory is beautifully reviewed in this paper by Kapusting and Seiberg of 2014. So I refer you to that for how to do that, and I will be relatively quick in the discussion. But essentially, the idea is that this theory does not have any local operators, but have extended operators, some sort of generalized Wilson lines. And since the two factors here are two forms, so then we have an electric generalized Wilson line and a magnetic generalized Wilson line. And we have R of those because we have R in equivalent U1 fields on the Coulomb branch. Now, if you study these Wilson lines, you will find that in the Hamiltonian quantization of this 5-dimensional theory, they satisfy a Heisenberg algebra, which has exactly the feature that we want. So in the 4-dimensional Hilbert space, it will pick up slices, and according to the intersection pairing of these surfaces, we will see that these lines are not commuting. And if these nks are not all identically equal to 1, then this is a non-trivial Heisenberg algebra that give rise to a higher dimensional Hilbert space of states. So this is exactly the Heisenberg algebra that we obtained from geometric engineering, and it was beautifully explained in this paper by Iñaki, Ben, and Diego of 2019. And we also have some version of that in M-theory in our paper from 2020. And with this, we can check many examples explicitly if we know the 4D n equal to 2 spectra. And exploiting this technique, we recover field theoretically our results from geometric engineering. So as an aside, this also indicates that all the operators for this AN-1 Argyres-Douglas theory are kind of singlets with respect to this one-form symmetry of SUN. This kind of is a way of arguing and explaining that paradox. So in order to capture the charge lattice of these theories, we exploit a technique that goes under the name of BPS quivers, which was developed by Alim, Ceccotti, Cordova, other students of Vafa at the time, Spavodi and Rastogi, that are probably now multimillionaires, and Vafa himself in 2011. I would also want to mention a very nice paper by Denef of 2002, where he kind of foreseed this type of application of quiver quantum mechanics. And of course, I have to advertise my old paper with Sergio of that same period. So exploiting these BPS quivers, we can essentially, what are BPS quivers? BPS quivers, you should think about them as if they are supersymmetric quantum mechanics that govern the stability of the BPS states for the n equal to 2 theory. So you think about describing the stability of a state in terms of the quantum mechanics that lives on its word volume, on its word line. Since this is a particle, it has a word line. So the resulting picture is some sort of a molecular model of BPS bound states, in which you have some generators for the charge lattice of your theory, which are bounded by the Dirac pairing. So what keeps the BPS bound states together is essentially a spin orbit coupling, if you wish. And this is more or less this molecular model of BPS states is what we use in our paper with Iñaki to have access to the generators of the lattice for all these examples. So as an example, let's discuss this 4D equal to 4 SUN, so to see if we can recover the result that was obtained holographically. Well, in fact, we will look at 4D equal to 2 star, because in that case, we have a BPS quiver description. So how is the BPS quiver of SUN obtained? So you remember we discussed SU2 before, and if you look at the generators in this Cyber-Witten basis of states, they have a Dirac pairing which is 2. So each of these subquivers with 2 arrows represents an SU2 factor of the gauge algebra, if you wish. They are like the monopole and the dion in Cyber-Witten. But then, since this is an SUN, then these SU2 subfactors are all interconnected. There is some Dirac pairing between the various generators for the various SU2 subfactors. And since this is n equal to 2 star, we need to add an extra charge corresponding to the adjoint hyper in the theory, which is connected to the quiver according to the representation theory of SUN. So you see, to connect this extra charge to this quiver, I'm using the fact that the adjoint of SUN is like a product of the n with the n bar representation. So from this graphical perspective, we can compute the Dirac pairing from reading it off from this. And if we perform this procedure to map it into a Smith normal form, this is the result that we obtain. And you see here, we have a matrix that is in block diagonal form. The only elements on the diagonal are these 2 by 2 blocks. And almost all of them are trivial, all have this nk equal to 1, but one, the first block has an nk which is equal to n. And then there is one last block, which is a 1 by 1 block that contains a 0 that corresponds to the fact that this charge lattice has a flavor symmetry generator, which is the U1 that would rotate, give rise to the mass to this adjoint hybrid. So to extract the pairing that we need to plug into our 5D theory, we need to focus on the 2R times 2R part of this matrix, and we get this Q tilde alpha beta. I think that was calling Q tilde alpha beta previously, and the result is precisely a term which is the same as the one that we were expecting from holography. So out of this construction, we get exactly the same term, which is good. This is a consistency check of that result. And of course, in this case, since it's a gauge theory, we knew that this was the gauge theory that covered the global structure directly from this paper by Kapustin, Seiberg, Willett, and Gaiotto on generalized global symmetry. They compute this from the perspective of the ultraviolet theory, but in our case, we can recover it also from the perspective of the infrared one. Many more examples of 4D n equal to 2 models can be found in the paper. We essentially discuss schematically all possible Lagrangian gauge theories exploiting these techniques, and all the 4D n equal to 2 theories that are obtained from 2B on hypersurface singularities. They can be treated uniformly in this way, and the result matches with this. And also more theories. There are also theories that have BPS quivers, but they don't have an engineering in terms of a hypersurface singularity. Also, those are covered by this trick. So the results also extend to 4D-KK theories, exploiting 5D BPS quiver to capture the relevant Dirac pairings of the resulting models. This is something that was done in this paper with my student and my collaborator in Uppsala, and also with the student of Jonathan and Miriam and Jonathan himself. So as an example, we can think of the E0 5D CFT, which was constructed by Seiberg and also by Morrison and Seiberg, exploiting geometric engineering explicitly. So in this case, the quiver has a structure which has only 3 generators in the charge lattice, which are interconnected by 3 arrows, which means that the Dirac pairing between each of the generators is 3. So this is a theory that is intrinsically non-Lagrangian. It's very hard to build this theory exploiting Lagrangians. And exploiting our trick, we get this Q tilde matrix which has a 3 and a -3, and therefore the resulting 5D TFT is one of this BF theory with a 3 in front now. And this is consistent with the prediction that this E0 theory has the same global forms as an SU3 theory, which was a prediction in the paper that we wrote together with Iñaki. So this is an example of how this type of techniques also generalizes to this class of models. And many more examples of 5D CFTs can be studied in this way, reproducing known results and predicting new ones coming from quivers that are obtained from exceptional orbifolds of C3 mod gamma, where gamma now is a discrete subgroup of SU3. These quivers were worked out by Lawrence, Nekrasov, and Vafa in '98, and simultaneously also by He and Hanani. And the results about the global form symmetries of these models were also obtained by Tian and Wang in 2021. So similar computations generalizes directly in 5D and 6D, and in those dimensions we get terms that have the schematic form. So these are BF theories that give rise to global structures for a Q form and D minus Q form symmetries in D dimensions. So for example, in 6D 2,0 theories, one has Q is a 2 form, and one obtains a term like that, which is responsible for the relative structure of the 6D 2,0 theory if, as a Q tilde alpha beta, one chooses the Cartan matrix for the corresponding gauge group. In 5D, you have similar terms involving one-form symmetries and magnetic 3-form symmetries. Magnetic 2-form symmetries. And so what I wanted to stress is that so this IR perspective also elucidates this interplay between relative quantum field theories and genuine, non-genuine extended operators, which was also discussed in this nice paper by Bardwaj, by Laksha, Simone, Max, and Sakura of last month. So this is no, sorry, of January. The main message is that these global structures are really everywhere. And in a sense, if you think carefully about what we discussed and about the analysis that we have carried out, even Maxwell theory itself has more global forms. In the moment we relax this Dirac quantization condition, in the moment in which we relax that, in the moment in which we start allowing fractional charges, there more choices become available, and also Maxwell theory becomes a relative theory. In fact, it's probably the most relative theory of them all. However, a caveat that I want to emphasize now that we are close to the conclusion of the talk is that at present we don't recover the whole symmetry TFT from the infrared. The only term that we recover from this type of approach is this term which is responsible for the naive global structure. Right? This term which is responsible for the Heisenberg algebra that we of non-commuting fluxes that we found in M theory or in string theory, geometric engineering. So this is just the tip of the iceberg, and there are many more developments ahead in which the interplay of the symmetry TFT with the other various background fields that can be turned on for the theory of the boundary can be exploited and elucidated. So stay tuned, and with this I thank you for listening to my seminar, and if there are questions or more time for discussion, that's probably a good moment.
Okay, great. Thanks very much. Let's thank Michele for a very nice talk. Other questions? Just unmute yourself and shout. So how would you generate, for example, other anomalies or topological couplings, right, in the symmetry TFT from this perspective? So say something like a B2 cube type anomaly in 5D that you can calculate geometrically from the boundary, but I guess you could also ask, how would you compute it from this sort of Coulomb branch perspective?
Well, this is a very nice question, Sakura. I mean,
and the BPS cover presumably encodes this also somehow.
About the B cube coupling, I'm not sure that I know how to do it. One thing, for instance, that I want to emphasize, for instance, in this action, you see that for instance, if you have some zero form symmetry, you could add to these actions term involving backgrounds for the zero form symmetry. And that's a term that we are currently investigating with my students that might be accessible from this infrared perspective of the of the quivers. For a B cube coupling, I don't know. It might involve some computing explicitly some contact terms. It would be very interesting to see. But the thing is, I think that in a sense there is somehow a very close interplay between the way in which string theory sees the structure of higher form symmetries and this infrared perspective, because often in geometric engineering we engineer consistent Coulomb phases, and then exploiting the consistency of geometric engineering, we flow backwards along the RG flow to some fixed points, right? So that was for me and Iñaki, that was the starting point in the logic. So if we can recover this from string theory, then we must be able to recover it directly from the Coulomb branch. But for higher order terms, that's a very interesting question. I don't know how to do it.
Because in fact, if you start with some supergravity theory, right? So you mentioned this holographic picture. So when you actually look at some gauge supergravities, you get these nice BF type couplings, but actually you get much more. And a lot of these couplings, you don't really know what they correspond to. These are some topological couplings in your gauge supergravity theory. So there you seem to have sort of a surplus of all these couplings, and it would be interesting to know sort of what they correspond to.
Is it possible that they kind of control the mixing of these various
yeah, I mean, there are lots
Eiger
of
form
sort
factors?
of zero forms and yeah, type Chern-Simons type couplings, of course, but also yeah, all kinds of higher couplings that mix various 0, 1, 2, 3, whatever forms you have. So
that's probably,
yeah.
I mean, if I have to think about a possible intuitive interpretation of those might be the ones that are responsible for this higher group structures that the geometric engineering can kind of detect from.
Yeah, I don't know. I think that's when it comes into it, but I think it's not just that.
It's not just
right?
that.
It can also be just Hopf anomalies. But yeah. Anyway, are there any other questions? So I can see Laxa is unmuted, Fabio is unmuted.
Yeah, just a comment. They might affect the global structure, right? These terms.
They could correct the Heisenberg. They could give rise to extra source term that changes the Heisenberg algebra.
I suppose you have a B cube term.
This is very interesting. As I emphasized, right, this analysis is just recovering the naive Heisenberg algebra that we got like a couple of years ago. And there is definitely a possibility of improving this analysis and adding extra terms which can capture more subtle feature of the symmetry TFT. But I emphasize again, it would be very interesting to have this other perspective, right? This some sort of a gauge or a field theory kind of way of arguing about this.
So what happened to this ZN1 form symmetry that was missing in the IR at the Argyres-Douglas point?
That one. So the idea is that if you compute the spectrum of the states that become massless and give rise to the Argyres-Douglas dynamics, they happen to be all neutral with respect to the one form, the ZN one form symmetry of the SUN theory originally. And so for that reason, eventually, the Argyres-Douglas theory doesn't have a ZN one form symmetry. But you need to explicitly, it can be explicitly checked. You just write down the spectrum of states that become massless at the Argyres-Douglas point, and you find out that they are neutral.
Right, but there are these line defects which are associated to the ZN1 form symmetry in the UV, which cannot end. Right, and where are these lines when I flow to the IR? What happens to them?
They become a decoupled sector, right? So there is, when you flow to the Argyres, this is a, in a sense, this is related to also this comment by Fabio previously, right? How can you match the anomaly or the symmetry from the UV to the IR? In this case, if you start from the UV and it is the SUN theory and you flow to the Argyres-Douglas point, there is a whole decoupled sector that splits away from the Argyres-Douglas theory, but you have to include it in the boundary. They kind of split one from the other.
But what is the theory which is described by this decoupled sector?
Yeah, good question. It's a good question. I don't know.
So it needs to have ZN1 form symmetry. Right?
Yes.
And, I don't know. So if you start with a ZN1 form gauge theory, then you get Zn times ZN1 form symmetry.
Yes.
So what is I don't know an example which will have just a ZN1 form symmetry. And
it's a very good question. I don't know. I mean, I was already happy in checking explicitly that the states that contributed to the EN theory were neutral with respect to the one form symmetry. But you're right. There is the question of what happens to the rest. It's a good question.
Right. So that's why I asked the question before. That's because I mean, I think it might. I mean, this method might be leading to interesting, like implications also for those sectors.
Yes. It's a very good. It's a very good point. I don't know. I have to be honest. I don't know. I haven't thought about it. So it's a very good point.
Thank you.
Any other questions? If not, we'll just thank Michele again, stop the recording, and then you can ask all your questions that you didn't want on record. So thanks again. It was a really nice talk.
Thank you.
And I'll stop it here and you will stop it there, I think, Lakshay. Okay.
I can stop.